In the last video, we had a look at the physical significance of the gradient for certain functions. In this video, we're going to look at how you can determine what a function is that tells you what the gradient is of another function. And we call that differentiation. Now, differentiation is useful when you have continuous changes. You can see here the graph s versus t is continuously changing. It's not a series of discrete changes. Well, let's just have a look at this case to start with. We want the gradient of this green line, because at t prime, the gradient of this green line will tell us the velocity, and we looked at that in the previous video. If I take some point a bit further than t prime, let's have that extra bit of time, I'll call that e, then you can see the gradient is slightly too big. If we just take the points, the top and bottom here, take the difference in the y-axis, divide it by the difference in the x-axis, the gradient's a tiny bit too big. But can you see that the smaller e becomes, the closer that line will become to the green line? That chord connecting this top point with this bottom point gets a gradient closer and closer to the gradient of the green line, the tangent at t prime, as e approaches 0. Well, the gradient, so delta s divided by delta t, is this difference. This top point here has an x-coordinate t prime plus e. And the y-coordinate, we can use this equation to calculate. That's what s of t is, a function of t. So displacement as a function of t substituted in here to find the y-coordinate is a multiplied by t prime plus e squared. Whereas for this point down here, the x-coordinate is just t prime, and the y-coordinate is just a t prime squared. Again, we've just used this equation here. So a gradient is a difference in the y-axis divided by a difference in the x-axis. So we can calculate the gradient of this chord. And as e becomes smaller and smaller, the gradient of this chord gets closer and closer to the gradient of this green line. The gradient of this chord is the difference between the values on the y-axis divided by the difference between the values on the x-axis. The difference in the y-axis is the final value on the y-axis, which is here, minus the initial value on the y-axis, which is a t prime squared. This part came from here, and this part came from here. We then take the difference between the values on the x-axis and put those on the bottom. The final value on the x-axis is t prime plus e, and the initial value on the x-axis is just t prime. Now the denominator is quite easy to tidy up. T prime minus t prime, that just cancels out and we're left with e on the denominator. We can multiply out this bracket here. So t prime plus e squared, we get this. T prime multiplied by t prime is t prime squared. E multiplied by t prime is et prime. But of course we've got a second et prime here, and that's why we have two et prime. The final term is this e multiplied by this e, giving us e squared. So the top of our fraction, the numerator, starts looking like this. Now we can multiply out this part here, multiplying each of those terms by a, and that gives us this term across here, which was multiplied through that part by a. A times t prime squared is a t prime squared. A times 2et prime is 2ae t prime. And a times e squared is ae squared. And you can see we've got an a t prime squared and a minus a t prime squared on the numerator, so they will also cancel. And our expression becomes this. Now both of these terms are divided by e, so we can just cancel one of those e's out. And we are left with 2a t prime plus ae. Now as e becomes smaller and smaller and smaller, this value here, which is the gradient of the chord, gets closer and closer to the gradient of the tangent when t equals t prime. And so we write that like this. As e approaches the limit that, e equals 0, then we stop writing delta s by delta t, and we start writing ds by dt. The d indicates a very, very small change, a continuous change, an infinitesimally small change. whereas a delta indicates a larger change, a discrete change. So ds by dt, remember that's the limit where e approaches 0. This term here approaches 0, and therefore all we're left with is 2at prime. And you can do this for loads of functions. I mean, it doesn't really matter what the function looks like. You could use the same approach. So let's run through this again, but this time let's have the displacement described by this equation here. Displacement is a function of time, but that function is some constant times time cubed. But if we want to know the velocity at time t prime, then we need to know the gradient of this tangent. I know this isn't a t cubed graph, doesn't matter. We use the same principles. As before, for this point here, its coordinates are in the x direction, t prime plus this extra bit e. In the y direction, we can use this equation here. And we get this expression that I've written here. Missed a little prime off there. And we could do the same thing for the first point, just like that. Now our gradient of the chord connecting these 2 points will get closer and closer to the gradient of the tangent at t prime as e approaches 0. Here it is written out again, where we have this term is this, we have this term is this. The final value on the y-axis minus the initial value on the y-axis. And just as before, final value on the x-axis minus initial value on the x-axis. And now we do exactly the same thing we did last time. We multiply out this bracket. I've just included there how to multiply out that cubic. And you can follow through those steps yourself. This is t prime plus e multiplied by t prime plus e all squared. And we already calculated what t prime plus e squared was. It's in these square brackets. So we just multiply that bracket out. Now when you multiply out that a, it looks like this. It looks very big and complicated. But an awful lot of this is going to cancel. Starting with the denominator, we can cancel those. Then we look at the numerator. A t prime cubed cancels with minus a t prime cubed. We've got 1a e t prime squared here and 2a e t prime squareds here. So that makes 3a e t prime squareds. And we've got 2a e squared t primes here and 1a e squared t prime here. And together that makes 3a e squared t prime here. And of course we've got a e cubed there, which stays where it is. Just as last time, we can divide through by e now because there's an e on each term, which gives us this expression here. And then remember, we are using the limit that e approaches 0. And we end up with this line at the bottom here. E approaches 0, so this term and this term disappear. And we're left with this term. And we can take any value of t. T prime could be any value, so I'll just leave that as t. S is a function of t. So with just those two examples, we saw that d by dt, so the first derivative of a t squared, became 2at. And the first derivative of a t cubed became 3at squared. So in general, we can write that the first derivative of any function can be found by multiplying that function by the power and then reducing that power by 1. And in the next video, we'll have a look at a few more examples of where you can use this.